Okay, so here we're going to go through our panel code or a sample source panel code. So what I'm going to do is show you my source panel code. Basically, it's all written in MATLAB. It is kind of an angle where we have an option to go between a cylinder or an airfoil. You have some parameters on size, you have number of paneling, free stream velocity, and these sorts of things. So if we kind of go back to our potential flow theory, what we're doing is we're adding potential flow solutions for a uniform flow. So this one, and sources, and these sources are placed around a panel. So if I could kind of sketch it out, we have a uniform flow. So really what we're focused on too is this one at an angle of attack of 0. So we have infinity. And then we have our airfoil, and we're given panels that discretize this airfoil. And I'm drawing it really crudely so we could easily see these. And in each panel, we need a ds and a normal vector. Just a comment, you typically have panels numbering from 1 to 2 to 3, 4, 5, 6, and you have to come back here for 7. And then what we also have to do is define a control point. So control points are the center. That's where we define the normal vector and the flow tangency conditions. And we have here, we have the vertex -1. So this is I control point. It's going to be 6. Here it's going to be 5, 4, 3, 2, and then 1. And that's because we're working on these control points are at the centers of the panels, and there's always one extra vertex. So this is kind of the gist of what we're doing. So at each one of these control points, we have a source, and it's spewing fluid out. And we combine this source with this free stream velocity at all the points to ensure flow tangency. Okay, so what do we do here? When we do this in actual code, this is kind of the process we have. Here we have our free stream velocity that specifies our free stream velocity component. Then there's this part of the code. This is how I did it. And this part is really relevant to forming geometry. You can see it's about 40 lines of code. And this is what I did to generate the geometry. So I had an option for a cylinder. And I have an option for, okay, if I'm a cylinder, how many, I wanted to find a delta theta. So how many increments do I break it up into? Then I go through and define basically a vertex. This is the first vertex. And I increment it by d theta. And I define the vertices on each side. So you can kind of envision this as here at this point in the code, we define the first vertex, which is right there. And then we loop over and we go d theta. This is the second one. Our panel is constructed there. Here's our third. And our next panel is constructed there. And what these things are doing are that we're defining these points right here, not yet our control points. And when you go through the whole process, you'll generate a circle. And each one of these are generated by d thetas. Okay, so that's our cylinder. We also have the airfoil. So it's an NACA airfoil, 0012 airfoil. Here it starts at the trailing edge of the airfoil. So we start right here. This is our coordinates. This is at 1. This is 0. And it starts the first point here. And then what you can see it does is it finds a theta to the center of the panel. So hold on, you can see. So what it does is it uses, I don't know how clear this is, but it's basically defining the circle here, and it's defining thetas here, and each one of these thetas gives us a different x direction or x location, and the y location comes from, so here 1 is x and then 2 is y. It comes from this equation of an NACA airfoil. And when you reconstruct it, you end up with your NACA 0012 airfoil. That's a really bad drawing of it, but this is what it ends up giving. So that was the approach I had taken. Okay, so regardless, that's just geometry. It doesn't get to the core of the code. The core of the code is right here. These few lines. And one of the things I tried to do was put these into functions. This is good practice to keep it into functions so you can kind of work with it a little bit easier and kind of focus your results. Okay, so what does this do? It has one part that computes control points and the normal vectors. So the input is the vertices. The output is a control point, a normal vector, and a size of the cell. So the control points are literally, start sharing again. The control points are literally, so these are our vertices. Let's say that this is for a cylinder. And we have these vertices. That's vertex 1. And this is 2. You can see this is the mean. So it's going to be this point. That's going to be our control point. When we go to the panel length, it's going to be given by essentially the magnitude of, okay, so you can see this is the increment of the vertex. So this corresponds with that point, and this one corresponds with this point. And what we do is we just shift around each panel. Okay, so this one is the length of the panel. You can see this is the difference in x locations and the difference in y locations. So if this is a panel, it's that length squared plus this length squared. Maybe if I could color coordinate. So that's that length. This is this length squared root. And that overall sum just gives us the magnitude of the size of the panel. Okay. The next thing that we have is the normal vector. How do we get that? So we have a given panel, and we're looking for the outward normal vector. So keep that in mind. It's very important. And the normal vector in general is given by essentially it's given by, so it's a normal unit vector. And what you do is you take, so the component, this vector is going to have a component in the y direction that is consistent with basically the change in y direction going from this to this with a negative sign, right? So if we, so the change from, So you can see that that change is this direction, but we need it to be outward. So we have this negative sign here. And then we have the change in X, which is that direction plus that direction. So it's the positive side. And it's consistent with everything we're drawing out here. So the sum of them, so the sum of these two vectors gives us our normal vector, but this is basically our normal vector divided by the area. So that's what this term is. So this is about as hard as it gets. We return all these to the solution here. We can see that we have captured them in our code here. Then we develop the influence coefficients. The influence coefficients basically utilize center, the control points, the normal vectors, the size, and the infinity. What this did in my code is I had it count the number of panels and the number of directions, just in case, pretty much just 2 here. Then we loop over the panels and look for the panels of interest. Okay, so we have our B vector. That's the first one. So remember, what we're doing here is we have, so say we have a cylinder and we're focusing on this panel, we want flow tangency. And we're saying that flow tangency is free stream velocity. It's the condition where the dot product of velocity and the normal vector are 0. So we have V dot N at a given panel. I'm just going to say that equals 0. V is given by the infinity plus the sum from I equals 1 to N panels, the induced. If we pull up our notes from before, what is the induced? We can see it in this section, right? Our induced velocity is from a given panel is given by what we add here. So remember, our panel has a length, and we're approximating as a point with and our source is the length of the panel times our local source strength. Here's kind of that same representation. This is V at the flow tangency constraint. When we approach ourself, we have this section. What we're building in this code for the influence coefficients is this. It's our radius between, this is basically influence on itself. And this is an influence in terms of, a radius 1, the distance between, so it's this vector. Maybe it's easier here. So radius 1, 2 would be the distance between source 1 to the point 2. So pulling this back to our code, we can come here and we can kind of see what's going on here. Oh, wait, let me just clarify one thing. So we have this equation for flow tangency, and we have it for each point. What we end up with is a matrix. Let me see if I can kind of describe it here. So our matrix elements, this is known. This is known. This is known. So if we were to write this into a matrix, we lump this into B. And again, AX equals B. This and this form the X terms. And these form the matrix terms. Actually, this and this. Oops. So you can see that in, see if I can clear these. You can see that our A matrix is basically composed of these terms. Our X matrix are the source strengths, and our B matrix ends up being what has zero dependency on what on the geometry or the free stream conditions. So that's where that B matrix comes. Yeah, so we could see in our B matrix, it's the dot product of the normal component of V infinity. And then we loop over with a nested loop. So it goes over I, and then goes over J, and we develop the rest of the terms. This term here is what happens when we induce flow in ourselves. It's basically this term. And then this term here is the size times the dot product of the radius between points 2 and 1 and the normal vector 2 divided by radius magnitude. So you can see this length, the dot product, and 2 pi radius magnitude. So here's where that 2 pi comes in. So we fill this matrix. So instead of a 2 by 2, it's a at number of panels by number of panel matrix. We solve for this. And you could see where this solution process is right here. Okay. Once we solve for Q, we basically solve the system. And these 3 lines are the core of the code. Thereafter, it's how do you process it to get it right? And I'm not going to go through all the plotting processes, but when I go through and plot it, here, this is a case where we have let's switch to a cylinder first. So this is where we have a cylinder. You can see we have a pressure distribution. I will note that in the pressure distribution, what we did was reconstruct the velocity. So here's this reconstruct velocity. It loops, it basically sums all the Q's times S's dividing by these so that it can reconstruct the velocity based on all the different influences at a given point. And we reconstructed on the surface to obtain this. If we zoom into, let's see if for some reason my zoom's not working, edit view. And let me just coarsen this just to see. So if we go to a very simple case with 5 panels, we can see we have normal vectors. It's a little bit skewed, so it doesn't come out looking normal, but it's normal. And these, so the blue are normal vectors and the black are flow tangency. You can see we're satisfying all the boundary conditions and we're getting these resulting pressure distributions. The next thing we could do is switch over to an airfoil. When we go to an airfoil, it only has 5 points, so it kind of flattens the leading edge. Go to something like 201 points, and we see we have a very clean looking airfoil and a nice looking pressure distribution. So that's kind of a summary of where we are and how to go through this. I encourage you to dig through this and try to understand. I think the key things there are to understand are, understanding the whole discretization process, kind of get a gist for what's the difference between a vertex and a center, and why it leads to one that small change of one, and imposing flow conditions at the control point. Then the whole concept of these influence coefficients. So understanding how these matrix elements are built up. And again, I encourage you to go through specifically this section of the notes to understand, we're working with source panels and influence themselves. Really, the core of what this whole code is right here. And that's pretty much the gist of it. Once you get it into that format, it's just a matrix inversion, which is real simple in the context of MATLAB. All right. That's pretty much it.